will be bringing exposure to our acid-base chapter over the weekend. I wanted to just start and kind of emphasize those things that I think are going to memorize. And there's many questions related to this very topic here, simply about what are the 7 strong acids? Because if I know those, I also know the weak acids. And then, of course, how do I recognize weak bases? Let's begin by emphasizing the names and the formulas of the 7 strong acids that I'm supposed to memorize. So first of all, we know HCl, and we know that's called hydrochloric. You need to know HBr, which is hydrobromic. I would emphasize again, sometimes the quiz questions have them by name, but sometimes they have them by formula as well. So I'm going to just write both. HBr, HI, which is hydroiodic, which is a fun name to say, hydroiodic, HI. And the one that I missed writing up here, I'm going to put down here, HF. Oh, no, I'm not going to write that one. 1, 2, 3. There's 3 binaries there, Cl, Br, and I, the halogens that are strong, not including hydrofluoric. We know that there is an oxy acid called nitric acid. That's a strong acid. We know that there is HClO3, which is called chloric acid. And then very close to that is the perchloric acid. These are all monoprotic acids. And then we said that there was one and only one that would be diprotic, and that we wrote as sulfuric, which is H2SO4, sulfuric acid. So if I know those 7 strong acids by name and by formula, I'm able to do so many things, such as categorize, is this strong, is this weak? I can label conjugate pairs. I can calculate pH directly from the concentration of the acid, just simply knowing that it's strong. So very critical to put those in memory, the 7 strong acids. Then we can talk about recognizing what our weak base is. And I just wanted to say anything related to an ammonia derivative that has a nitrogen, we know that that is going to act as a weak base, seeing that it can accept an electron pair. So anything with that nitrogen is going to be targeted. And then, of course, you can recognize weak bases as the conjugates of strong acids. And what I mean there, for example, since HCl is a strong acid, its conjugate base would be considered weak. So I say all of that to kind of share these 2 types of questions from our quiz. Okay, one quiz question asks, which of the following compounds are weak and which are strong? And then I had a second question kind of as a follow-up, style of question, where it's asking which of the following bases are weak and which are strong. Let me give you a moment to look at those formulas and kind of make your own guess on the notes that you're taking. Okay. Classify these strong or weak. And just so you know, when you go to take your quizzes for practice, or if this were an actual test question, just to kind of give you an idea of what the A, B, C, D, and the multiple choice format would look like, it would have like weak, 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 strong, 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 or any kind of combination thereof. So that's kind of what you're trying to do, is to choose the correct answer based on what they're labeling as strong versus weak. So with the first question, it becomes as easy as saying, okay, I have the 7 memorized. Are these one of the 7? Notice these happen to be by name. Nitrous acid is not the same as nitric acid, so don't get fooled there. Nitrous comes from the polyatomic ion nitrite. That's a weak acid because it's not one of the 7 strong. We recognize HCl. Okay, that's on the list that I have memorized. So that's a strong acid. And hydrofluoric, HF, is not one of the halogens that's considered strong. So you'd have to find the answer that went weak, strong, weak. That's it to that question. I think if I'm going to get fooled on this, what might happen is that I have in my head nitric, I can't remember exactly, and I get fooled thinking nitrous and nitric might be the same thing. But remember, us came from the polyatomic ion nitrite, and they are not the same. So now, what about for question 2, where you had, is this strong or weak for a base? And notice that they give me the language ammonia, not the formula. So I have to have that memorized as being NH3, ammonia. And fluoride is an anion, and then sodium hydroxide, NaOH, for that polyatomic ion, that base ion. So here we can see ammonia, we just said a moment ago, ammonia and any of its derivatives, we have to know by heart that it's a weak base. Fluoride is the conjugate base of HF, right? So this is the acid, this is its conjugate base. So that's a weak base. NaOH, well, first family metals hooked to hydroxide, we know those are solubly strong bases, so we'd label that strong. Let me give you a moment to see if this jogs any questions about how to identify a strong or a weak acid or base, and feel free to enter that into the chat if you have questions related to recognizing acids or bases being strong or weak. Any thoughts? Enter them into the chat or turn on your microphone, of course. All right, I think that's enough wait time. I don't see anything coming into the chat, so we'll feel free to move on. Again, never hesitate in putting something into the chat. I'm doing my best to try to watch that as well. Okay. Let's take a look at a next example. And what I've done is try to start from the beginning of the chapter, find an example, and we'll progress through the content that way. Here we're being asked to calculate a pH given a molarity of a base ion, potassium hydroxide. So a couple of things I want to note. KOH, I know as a strong base. Any first family metal, the alkali metals, attached to the hydroxide, we know to label as strong base. And when I say strong, I now realize that there's no equilibrium set up, that there's no need for worrying about a KB expression. Strong bases and strong acids, we know will have their pH calculated directly. So if I have a 6.5 times 10 to the -5th molar potassium hydroxide, the very definition of strong says that's giving me the molarity of the base ion. Now, the reason I picked this one is just to remind ourselves that when I calculate the negative log of the concentration of the base ion, I'm getting something called the POH, not pH directly. So I'll hit on my calculator. I'm going to hit negative log of 6.5 times 10 to the -5. And that gives me a value of 4.187. Now, I'll tell you, guaranteed on tests or the quiz bank, they're going to have that as a choice. You know, in the multiple choice setting, you'll see 4.187, and some students will get so excited that something matches their calculator screen on the answer sheet and they just select it and think they're done. But remember, don't fall for that trick. Bases have pHs that are greater than 7. So just mentally check, okay, this is a base, therefore I know my answer has to be above 7. So just make that quick exchange and take 14 minus that answer and find 9.8. I'll say 813. There's the pH of the solution. That's a number that makes sense for a base pH range. So this just a little practice with memorizing or knowing those pH formulas. You've been using them all module long, pH, POH, and turning them from one to the other. Questions there at all? Let me give you a minute to think before we go to the next slide. Feel free to turn on your microphone at any time and interrupt me. I think that's enough wait time. Here's our next example problem. Now this one seems easy at first, and I'm going to talk you through what might be the most common mistake. It reads, I have a solution with a pH given to me as 10.60, and I'm going to dilute that from 1 liter to 2 liters. What is the new pH of the solution? Okay, so it's a dilution problem. Let's think logically, just, no numbers yet, but if I add water to a solution, I'm diluting the solution. Would you anticipate the solution to become more basic or less basic by adding water? Perfect. Yes, thank you. I agree. Absolutely. The more and more and more water that I add to the solution, the more it should become closer to 7, the pH of actual water. So I know my answer needs to be less than 10.6. That's just me thinking out loud logically. Now, when I'm measuring the pH of the solution, and it is a basic solution, you are diluting the hydroxide concentration. So what I need to do to consider, if the pH is 10.6, I really want to keep track of the POH as I dilute the solution, because it's being tracked in terms of determining pH. So if pH is 10.6, the POH is really what I'm diluting. And I'm just going to say that's 14 minus 10.6, which is 3.4. So this concentration, I'm going to bend my laptop, the concentration of hydroxide is 10 raised to the negative 3.4 units. So I took my pH, converted to POH, and I'm working out to find the concentration of the base ion. So 10 caret key negative 3.4, and that shows me the hydroxide concentration as 3.98 times 10 to the negative 4 molar. Now we're comfortable with dilutions. We know MV1 is MV2. MV equal MV is a common formula we've learned for diluting. The molarity of the base ion was 3.98 times 10 to the negative 4 when I had 1 liter. We're diluting it now to 2 liters. So you can see the concentration essence is going to be cut in half. The new concentration, divide by 2 on my calculator, and it reads 1.99 times 10 to the negative 4. And if you remember, that's what we assigned to the hydroxide, because this was a basic solution. We added water. We need the molarity of the base ion to be half as much as the original solution since we doubled the volume. I can find the pOH from the hydroxide concentration. So I'll hit negative log that answer. And the H came to be 3.70. 14 minus that answer is going to give us 10.298. So I'll say 10.30. Now, remember the original pH was 10.6. So this number makes sense because the base pH dropped closer to 7, right? The pH goes down just as you had predicted. It should be less than original. The trick with this question was not using the hydrogen ion, but rather the hydroxide ion concentration. Let me model a common mistake, and we'll talk about how I know it's wrong. Do you remember when we were given 10.60 as our pH? One of the common things I see done is switching hydrogen ion and diluting that. So if I were to do this incorrectly, I'm going to show you how you know at the end you're wrong. 10 to the negative pH gave me my hydrogen ion concentration. And remember, that was in 1 liter. So you're diluting that. And when you divide that by 2, you get a number of 1.26 times 10 to the negative 11. And when you take negative log for pH, if I hit negative log of that answer, I get a number 10.90. Now, this happens to be a choice on your multiple choice because they like to make sure that if you get an answer that seems correct, it's, you know, you've done some calculating on your calculator there and you've got a number that matches, you're more likely to select it. How do you know that this is not correct? If I found that answer from doing an MV equal MV problem, how do I know that it's not correct? Well, you're actually telling me in the very first answer that there's no way by diluting. Yeah, exactly right, Ryan. Perfect answer. When you started with 10.6 as your pH, yeah, you're right. And adding water cannot make the pH go up, right? We already agreed that the pH had to go down. So if I forgot that I was working with a basic solution and I should be tracking the hydroxide ion for the dilution, and I went ahead and did my MV equal MV straight from pH, at the end I should go, well, that makes no sense. 10.9 is a more basic solution. I can't add water and make something become more basic. That would allow me to go back and say, oh, since I'm using a basic solution, the dilution has to focus on the base ion and not the acid ion. Perfect. That actually, you know, at first glance, that looks like a pretty simple question, but it has a trick. And I just wanted to grab that trick, is that if you're using a pH from a basic solution, perform your dilution from the hydroxide concentration. Perfect. Any questions on that one before we move on? Let me give you a moment of think time.
So I guess I just kind of got confused on how you were like using pH and pOH interchangeably, like with negative log. Like you can, it doesn't matter. It's not just strictly for pOH. You can use it with pH as well.
So good question. When I have hydroxide concentration, when I negative log, I get something called pOH. And if I have hydrogen concentration, I negative log and get pH. But when you say interchange them, they are pretty easy to exchange quickly because I know the sum of pH and pOH is always 14. So
Right.
if I take a little, so it's very simple to change one answer into the other quickly by knowing their sum. Is that what you're asking, or am I not hitting it exactly?
No, that was right. That made sense.
Okay, yeah. So real simple, if I found pH is 10.6, I just do a quick subtraction and now all of a sudden I'm at pOH. Good.
Okay, thanks.
Other question before we go on. Cool. Okay, again, don't be afraid to stop me. Here we have a question where I finally work a equilibrium problem asking about a KB. We're giving a pH of a 0.1 molar pyridine compound. Now, pyridine, I know is a base because I see a nitrogen in it. And just keep in mind that anytime you see a nitrogen, think of it as an ammonia derivative. That nitrogen, has 3 bonds and a lone pair. I don't really care what's attached to those 3 bonds. It's this part that's of interest in acid-base chemistry. So it's the nitrogen that lets me know it's acting as a base. Not to mention it's giving me a base pH number and it's asking me about a KB. So all of that information kind of just is useful to know. Pyridine is a weak base. When I write out my equilibrium, oftentimes I just take a shortcut and instead of writing C5H5N, I just let B represent base. So if I were to start with my equation, I would say, okay, a weak base is going to be added into water. Bases accept, oops, I just wrote N, bases accept a proton. So I form its conjugate acid and the base A negative. So my conjugate pairs always add water, base accept proton, the acid then donated the proton, so there's our equilibrium. Initially, we have a 0.1 molar base ion, and these of course would be 0. And it's telling me that the pH of this solution is 9.09. And what this actually tells me is the information for the at equilibrium, what those ion concentrations are. Why did I write A negative? I'm so sorry, folks. I meant to write OH negative. There's the base ion right here. I'm sorry that I noticed that. So thank you. I think A negative is what I write for acids all the time, A. So that makes it a little easier to see where the base ion is, the OH negative. So this would be a little margin math going on your calculator. I want to convert pH into pOH, and I'll do that with a simple subtraction. So the pOH is that difference from 14. I can raise 10 to the negative 4.91, which will get me the hydroxide concentration at equilibrium. So thinking about how this ice chart works, this right here, 10 to the negative pOH, is the concentration at equilibrium for that base ion. Alrighty. So when I hit that on my calculator, 10 raised to the negative 4.91, my screen reads 1.23 times 10 to the negative fifth, and that's this part of your ice chart. Now, once we have that box filled out, we know from last chapter how to just carry on and finish the rest of the ice chart. That this must have increased by 1.23 times 10 to the negative fifth. The BH positive did the same thing. In other words, the concentration of both of the ions is exactly the same. This must have went down by the same number. So at equilibrium, you have the difference between the two. Once we have that entire row filled out for KB, we already have what we need to calculate products over reactants. So the KB expression would simply be the hydroxide ion squared, because it's representing both the conjugate acid and the conjugate base, over the difference between the original concentration of 0.1 and that molarity we found for the base. And now it's just a simplistic calculation of products over reactants. And again, the reason I selected this was to remind us at equilibrium, the POH gives us the hydroxide ion. So let me hit that for us. -5 squared divided by the difference between the two. Wrong button, darn it. There. So my screen is reading 1.51, I'll say, times 10 to the negative 9th. And I'll see if anyone else got the same thing. Give me a thumbs up in the chat if you found the same answer as I did. My dog is snoring by my feet. How funny. You got the same, Ryan? Perfect. Friends, anything else on this question that you'd like to ask before we move to the next? Okay, sounds good. Let me go to the next example. Oh, yes, I wanted to include an example on a polyprotic acid. And this example quiz question allows me to do that. I'm given a number of moles of a diprotic acid, H2A, and I dissolve that into 250 mils of water. So I'm just going to quickly find the molarity, take moles per liter, and let me just do that quick for us. 0.43 over liters. This is a 1.72 molar solution of H2A. So that's the first sentence. The information gives me a diprotic acid, and then I worked out its molarity. Okay. The Ka1 of the solution is given, as well as the Ka2. Remember what that means. In the first ionization, the diprotic acid loses its first proton, and when it loses the first proton, forming a conjugate acid-base pair, it has something assigned to it called a Ka1, and that value is 1.0 times 10 to the negative fifth. Ready? I'm going to leave a little room for the math, and I'll come down here and say, when the second ion is removed, a second process, removing that ion, forming a conjugate pair of A-2 and hydronium. Removal of the second proton is given the Ka2 value, which is always significantly smaller. Here it's 1 times 10 to the negative 10. So that's kind of the second sentence information. It asks us ultimately to calculate the concentration of A-2. So I'm just kind of putting this as my ultimate target right here. What is this concentration? From the information, we were given H2A's concentration of 1.72. And let's just let the letter X represent the concentrations at equilibrium of HA and H3O+. And we understand by now that when we have such small values of Ka, I can just toss out the value of minus X and make the math a little more simplistic. We called that the 5% rule when we were going through our notes together. So I can find the value of X by taking Ka1, setting it equal to X squared over 1.72. And all I'm saying is, if you were to solve the equation where you had the minus X in there, you'd end up using the quadratic equation. Learning that the value of this X is so significantly small, right, it's negligible compared to the original concentration, that it's okay to just toss out the value of X because it's not going to change the overall answer. So that's what I mean by that 5% rule. I'm going to estimate the value of X by tossing out the quad formula. We went through that quite thoroughly in the notes, but let me know if you need me to expand on that a little more. I'm going to cross multiply 1 times 10 to the negative 5 times 1.72. I'll take the square root of that answer to find the value of X. So right here, when I solve for X, let me change color. When I solve right here, X on my screen came out to be 0.00415. Going through that, just to kind of show what I did, I found X squared by multiplying 1.72 with the value of Ka1. And then I just took the square root of that answer to pull out X. So that was me solving for X right here. Now remember what X stood for. X stands for the hydronium ion as well as HA negative, right? Those are the same number in this solution. So when I come down to the second ionization, the value of HA and the value of hydronium are exactly the same number. We found them to be 0.00415. What we're looking for now is X, the A-2 number. A2 set equal to the value of A-2, the value of the hydronium ion over the concentration of HA negative. What happens in second ionization, and this is always true, the concentration of these conjugate pairs, the H plus and the HA negative, they're always going to cancel. So the value of Ka2 is going to be equal to second ionization, A negative 2, that anion of the original diprotic acid. 1 times 10 to the negative 10th would be your value. When I see this type of problem, I'm looking at a diprotic acid and trying to find the concentration of the anion in the second ionization. I don't even need to do any math, my friends. It's as easy as saying, I know the answer is going to be Ka2. I know that, and I just proved it to myself by doing a two-step ionization problem. But that will always hold true. In a diprotic ionization, Ka2 will equal the anion in that second removal. What do you think about that? Any questions, comments on that problem? If this question had asked for pH, it did not, but if it asked for pH, how many ionizations would we go through to find pH? I don't care if it's monoprotic, diprotic, or triprotic. pH is always found from that first ionization. So if it had asked me for pH, this is what I would take negative log of, 0.00415, and I would have the pH of that solution. So if it had, and this one didn't, but sometimes they ask for the pH, you're just going to find that first hydrogen ion and take negative log there, and you'll have the pH of the solution. Polyprotic acids. So I went ahead and found an example here where this time I give you a triprotic acid and we have to go all the way to phosphate. Kind of go through what this is saying. I have a triprotic acid, H3PO4, and it's asking me about the phosphate PO4 minus 3. Since that's removal of 3 hydrogens, I want to emphasize that it's not as easy as saying, oh, it's just that number there. It only works had they asked you for a 2-proton removal. Then it's really no math. But if they have you removing all 3 protons of a triprotic, you have to go through all 3 ionizations. So I just wanted to emphasize that. How do you feel about solving for this type of problem? Do you want to see that worked out, or was the previous example enough? What do you think? Anyone want to see this one, or should we go on? Okay, no one's answering. So I'll take that as we're all set. If you have time, you want to stay after, we can come back to it, but I'll go on to a different type of problem. My next example focuses on salts. The very last part, well, it was the discussion forum for this week as well. Which ionic compound forms a pH of neutral aqueous solutions? So with this example, I'm making us remember a little bit about hydrolysis of salts and the ability to recognize if the cation comes from a strong or weak base, and if the anion comes from a strong or weak acid. So let me give you an example just by working through LiCl HClO4, lithium perchlorate. The two ions that make up this salt are the lithium ion, which is the cation, and the anion, which is called perchlorate, ClO4. A salt, the definition given to a formula unit where we have a positive and a negative ion bound together to create a salt. It's not an acid, it's not a base, so therefore the combined ionic compound is called a salt. Anions come from parent acids. The cations come from parent bases. So when I was talking in the lesson about parent acid and parent bases, I'm just putting an OH on the first ion and an H on the second ion to form a parent acid and a parent base. So we have to ask ourselves, is it strong or is it weak? If it's a strong parent base or a strong parent acid, there is no hydrolysis and therefore no effect on pH. If it has a parent that is weak, the answer is yes, it will undergo hydrolysis and therefore will affect the pH. So we recognize this as a strong base, so no hydrolysis. No effect on pH. HClO4 is one of the 7 strong we had memorized, so no effect on pH. So neither the cation lithium nor the anion perchlorate will undergo hydrolysis, so I know right off the bat the pH of this solution will be 7. There's no effect on pH if both ions come from strong parents. What about NaHCO3? Sodium ion, the hydrogen carbonate ion. The parent base would come from sodium hydroxide. The parent acid comes from carbonic acid, H2CO3. See, I'm just adding another H on to find the parent acid. We recognize the base as strong. We recognize this acid as not being strong, so therefore we know that it's weak. So this is telling me that this solution will undergo hydrolysis. And when an anion hydrolyzes, which just means add water and form conjugate pairs, we know the solution will become basic. So this solution is going to have a pH greater than 7. This solution will become a basic solution. You can go through each of these salts and try to identify, are they being strong or are they weak? Here you can see you have a nitrogen derivative for letter C. Letter C, ammonium is the cation and chloride is the anion. The parent base is weak. The parent acid is strong. When a cation undergoes hydrolysis, we know that it will be an acidic solution. Prove that to yourself is that when you have the NH4 plus undergo hydrolysis, forming its conjugate pairs of ammonia and hydronium. So you can see that the positive ion makes an acidic solution, whereas the negative ion would make a basic solution. And again, here's the parent base, KOH. Here's the parent acid, HS negative. That's a weak acid. You know it will be a greater than 7. Same thing here, HF. That is a weak acid. Therefore, you know it will hydrolyze to make a basic solution. So this question really is just asking you, it's going to form a neutral solution, which is what this asked, right? Which ones are neutral? You're looking for the positive and the negative to both have strong parents. And as soon as you can recognize which acid is strong, which base is strong, you can find the answer quickly. It's really, you don't have to write out equations. You just have to find the salt, the positive and the negative, that have strong parents. Now, let me give you a minute to think about this in general. Feel free to turn on your microphone and ask me a question. And comments. Just take further examples. We can continue working and just see if there's anything else that you'd like to ask me. You're very quiet today, and that's okay. I just want to make sure that if you have a question, you feel confident to just turn on your mic or send me a message in the chat. And I'm trying to watch both, so if I miss it, please just let me know. I'll work a next example. This one is a problem given a methylamine, and the concentration of hydroxide is what's being asked for. The Kb for methylamine is given. Now, if I had no idea what methylamine is, it's a nitrogen-based compound. So we have this ammonia derivative. Here, the AM for ammonia derivative. So even if I don't know the formula for methylamine, that's okay. I just use the letter B to represent base. And so I can set up the hydrolysis by simply showing a conjugate pair between BH positive and OH negative. This chemistry is a Kb, so we have 4.4 times 10 to the negative fourth. The base is given to me is 0.05 molar, and we're being asked to solve for the hydroxide concentration. It would also be the same concentration as the BH positive. So given the Kb of 4.4 times 10 to the negative fourth equals to x squared, and we know that it's technically 0.05 minus x at equilibrium. And you could distribute that through and work out the quadratic equation, or you could toss out x and get a very close estimation, enough to find your answer, especially in a multiple choice setting. So that's truly a time saver. X being the hydroxide ion concentration. So this was a pretty straightforward, and yet, you know, I pulled from quizzes that had missed questions, and this was one of them. So again, it might seem simple, but it's always good to practice. I'll cross multiply, take the square root, and solve for x. And I did that. My screen says 0.00469, so I'll just round a little bit. Alrighty. You got it, Ryan. Perfect. Indeed. Yes. Good work. Any other problems? I think I found. Let's see. Yep, that's pretty straightforward. So I just did square root of 4.4 e negative 4 times 0.05, just answering a question I see in the chat. I cross multiplied and then took the square root to find x. Here's one that allows us to kind of put hydrolysis of salt in with a problem. So I have a compound called aniline hydrochloride. And again, I see this nitrogen there. And anytime I know nitrogen, it's some derivative of ammonia, and that's going to be a weak base. And they give me a Kb for it as 3.83 times 10 to the negative fourth. We'd like to know the pOH of this solution. The thing is that this is a salt. It's not an acid. It's not a base. I have a positive ion, C6H5NH3 positive, and I have an anion of Cl negative. I have to recognize that as a salt, meaning the positive or the negative ion will influence the pH based on hydrolysis. We know the parent acid of Cl negative is HCl, and we know that is strong, therefore no effect on pH. We know the conjugate of C6H5NH2 would be a weak base. We know that it's a weak base because of the nitrogen in the formula. That's an ammonia derivative. And therefore, yes, it will affect the pH. And it does so by just simply forming conjugate pairs. So of this salt, this is the actual chemistry that affects the pH of the solution. We have C6H5NH3 plus, that's the cation in the salt, undergoing hydrolysis, so I know to always add water. It'll form its conjugate base, and it will make the solution acidic, H3O plus. So it's a proton transfer from the conjugate pairs. At the beginning, we have a 0.716 aluminum hydrochloride solution. Let's let the value of the two ions be X. Interesting is that I'm given a Kb for this problem. However, when I make an acid solution, this needs a Ka, right? Anytime I have hydronium in solution, I have to convert the Kb into a Ka, which is easy enough to do by using the Kw for water. We know that that expression can convert one into the other. So Ka is needed. I know that because this is an acid. Therefore, that's acid chemistry, and therefore I know I must have a Ka value. Ion product constant for water, 1 times 10 to the negative 14th. I'll divide by 3.83 to the negative 4. Here I'm looking at the Ka is 2.61 times 10 to the negative 11th. Our Ka value we just solved for, 2.61 times 10 to the negative 11th, will be equal to x squared over 0.716. We cross multiply and take the square root. And x came out to be 4.32 times 10 to the negative 6 molar units. And this will be one of your choices on the multiple choice format, guaranteed. But do you remember, we let X be hydronium ion concentration. That's what X is, right? Hydronium ion. And what were we really being asked for? We're not done yet, right? We need the POH of our solution. Just try to scroll back up, right? We needed POH. So almost there, but not quite. Since this is the hydronium, I can negative log 0.32 times 10 to the negative 6 and get something called pH because it's the hydrogen. So I'll hit negative log of that answer. And this also most likely will be one of your choices on the multiple choice, but we know not to be done because we needed POH. So one last conversion, turning pH into POH, and we find 8.635. I'll just round 8.64 for that solution. So this one had a fair amount of chemistry to find out, first of all, are you recognizing a salt when you see one? And if you recognize a salt, you have to decide, okay, this is the guy that's going to influence the pH, the cation of a weak base. It influences by making this solution acidic. And ultimately, we worked for the POH by just doing this last conversion from pH to POH. Give you a moment to think. Any questions on this particular problem? That's a good question. Brian is asking, how do I know if it's an acidic solution or a basic solution? And this is the little trick. And if it works for you, great, but this is how my mind works. I know that when I have a salt, it's a positive ion hooked to a negative ion, right? It's a cation to an anion. The first position cation comes from the base, and the second position, the anion, comes from the acid. Now, what I mean by that is, let's say I have, ammonium chloride. Ammonium is the positive cation. It has a parent base. Chloride is the anion, so it has the parent acid. Now, in my head, this is what I do. The first position will make it acidic. The second position will make it basic. If the positive ion comes from weak, it'll make it acidic. A comes before B in the alphabet. It's just a little trick. And I can show you with chemistry is you're going to proton transfer, so you produce a hydronium ion. And here, when you proton transfer, you produce a hydroxide ion. In the positions, if it's acidic, it'll come from the positive ion. And in the second position, it will come from the negative ion. A comes before B. Way back when, let's see, if I back to an earlier question where I just had a bunch of salts listed, could have been ha. So let me clear the ink from the slide. And let's just say, yeah, so if it's a weak base, it'll make the solution acidic, and vice versa for weak acid, yes. So for instance, in letter A, I go lithium hydroxide, perchloric acid. Both are strong, so no effect. Here's NaOH and then H2CO3. This is weak. Since it's in the second position, I know it will make the solution basic. Here's ammonium, backwards. You got it. Ammonium is in the first position, so I know it will be an acid. A comes before B. This is weak, so I know it will be basic. This is the weak, so I know it will be basic. The only one in the first position will have a nitrogen in it if it's going to have any influence on pH. If you don't see a salt with a nitrogen in it, then no effect from the positive ion. That's kind of my trick, is knowing that if I can find a weak parent, if it's in the first position acidic, if it's in the second position basic, and it goes as fast as that then. Perfect. Other questions? General. I'll put together a second review session set for Saturday morning at 10 a.m. And again, if you can't make it, no worries, I'll send the link out. But if you have a question that comes up between now and then, please feel free to email me so I can be sure to include that in my review session. This was a great hour of practice, get you ready to start your first attempts at your quizzes. And good luck. I don't see anything else coming in the chat. Nobody's turned on their microphone, which is a good thing. I'll take that as a good thing, knowing that you have enough ammunition to get started on your quizzes. I'll hang out till the last person leaves. If you have a question for me, feel free to you're very welcome. Have a good rest of your day.